try to communicate with extraterrestrials. It's a bit like shouting across the universe with a sign written in sign language. Maybe elsewhere in the universe, on planets other than Earth, there are other forms of intelligence. But so far, the great silence reigns. And what if the fact that we haven't received any messages from extraterrestrial civilizations so far, even though there are hundreds of millions of potentially habitable planets in our own galaxy, is simply because space is so vast that no one can hear you scream? As you may have guessed, today I'd like to give you a sense of the immense challenge that any attempt at communication across the stars represents. Because it doesn't matter whether the message you're trying to share is an instruction manual for mastering one of the greatest advances ever made by a species in the universe, namely the raclette machine, or the blueprints for a particle accelerator. For your message to reach its target, you need to find a way to overcome the staggering distances that separate you from other star systems. Already, there's nothing new under the sun. The idea isn't new, and throughout modern times, many brilliant minds have come up with ingenious ways to overcome this vastness and give our voice enough reach to be noticed by hypothetical extraterrestrials. At the beginning of the 19th century, when people still imagined it possible for intelligent life forms to exist on the surface of the Moon, Mars, or Venus, because our telescopes had not yet revealed to us just how hostile these worlds are, some thinkers suggested producing intense and powerful light signals in order to make ourselves noticed on a very large scale. In 1919, in order to make contact with extraterrestrials supposedly living on the surface of Venus, it was seriously proposed to dig a whole series of trenches several hundred meters wide in the middle of the Sahara, and which together would form geometric shapes about 30 kilometers wide. Each of the trenches was then to be filled with water, on the surface of which large quantities of kerosene would be spread, which, once lit, would allow a signal to be sent every night. From the desert transformed into a sort of gigantic blackboard on which we could, at will, write with fire. A year later, in 1920, the mathematical genius Carl Friedrich Gauss proposed planting in the Siberian tundra lines of pine trees several kilometers wide surrounding vast expanses of rye and wheat, to create a geometric figure demonstrating the Pythagorean theorem. A figure so vast that it could be seen by possible Selenites, the supposed inhabitants of the Moon. None of these large-scale patterns drawn on the surface of our planet ever came to be. And with the development of electricity, people began to imagine other ways to get noticed. In 1874, engineer Charles Cross, convinced of the existence of Martians, tried unsuccessfully to raise funds to build a huge parabolic mirror, which was supposed to reflect and concentrate enough sunlight to draw figures on the surface of the red planet. The following year, in 1875, a Finnish mathematician with an absolutely unpronounceable name, Edvard Ungelberg Novius, considered creating a device containing 22,500 electric lamps. Lit together, they were meant to let people greet the Martians. Nearly 150 years after these approaches, which all remained as ideas on paper, our technologies have made giant leaps forward. And yet, paradoxically, the difficulties to overcome in order to communicate across the vastness of space have become even more complicated. Because today, we know that none of the planets in our solar system are inhabited by intelligent life. And to hope to be noticed by hypothetical extraterrestrials, we necessarily have to turn to very distant planets, planets orbiting stars other than our own. However, the space around us is so incredibly vast that it is absolutely unthinkable at the present time to send messages out into the cosmos using ordinary light signals like visible light. Because with the phenomenal distances that separate us from other stars, apparent brightness quickly fades away, like snow melting in the sun. In fact, the dimensions of space are so vast that only the most powerful stars are visible from a great distance. To be convinced of this, consider that the closest star to us, which is located only 4.2 light-years away from here, which, in cosmic terms, is like the house next door, isn't even visible to the naked eye. and it was only discovered with our telescopes at the beginning of the 20th century. And we're talking about a star here, whose brightness is certainly nearly 1,000 times less than that of the Sun, but still a star nonetheless. A celestial body that emits into space every second much more energy than all of humanity has consumed since the Industrial Revolution. So, aware of our limitations, we started exploring other ways to get noticed, some of which are completely crazy and involve communicating with nuclear bombs. In 1971, during the height of the Cold War, at the first conference aimed at thinking about ways to identify and contact hypothetical aliens, one of the participants suggested gathering all the nuclear warheads produced by the United States and the Soviet Union in space, and then detonating them all at once, and thus produce such a phenomenal amount of X-rays that it should be detectable by other advanced civilizations. The idea was to stop the nuclear arms race while at the same time giving a little wave to extraterrestrials. In the same vein, Andrei Sakharov, one of the most eminent Soviet physicists and a passionate advocate for nuclear disarmament, went a bit further by suggesting that all existing bombs be placed at specific locations in the solar system. Then, to detonate them following a particular rhythm, with the sporadic flashes potentially sending a simple message, making it possible to get noticed, like sequences of prime numbers using nuclear explosions. Very complex to implement and extremely dangerous, since sending a bomb into space requires putting it on a rocket, these proposals were never really taken seriously. In the following years, 4 different probes to the outer planets of our solar system carried with them gold plaques and discs on which a few inscriptions were engraved, intended for other civilizations that might have emerged in the universe. But these probes, drifting in the cold immensity of space and carrying with them a small piece of our humanity, are not aimed at any particular star system. And above all, they are so small and so slow compared to the immensity that surrounds them, that there is practically no chance they will ever be intercepted. To convince you that these messages in a bottle, sent out with no recipient, are very likely lost forever, I think a little reminder of the immensity of our own solar system is in order. This, to scale, shows the size difference between the Earth and the Moon. And here you have, still to scale, the distance that separates us from our satellite. To travel from our planet to the Moon, or vice versa, it takes a ray of light, the fastest thing in the universe, just a little over 1 second. To travel from the Sun to our planet, it takes 8 minutes and 20 seconds. To travel from the Sun to Neptune, the last of the gas giants, it takes almost 4 hours and 10 minutes. And to reach the limits of our star's gravitational influence and truly leave the solar system, light takes a year and a half. And the closest star to us is 4.2 light years away from here. The Voyager 1 probe, which took with it one of the gold records engraved for extraterrestrials, is currently the object made by human hands. The fastest of them all is traveling through space at the dizzying speed of 60,000 km/h. And yet, even though this speed seems staggering, it is still nearly 18,000 times slower than the speed of light. So, to cover a distance equivalent to the one separating us from the closest star, this probe would take nearly 70,000 years. That's a long time. And that's why, when we seriously consider sending messages into the cosmos, we always turn to light, which has the fastest speed in the universe. The problem is that to create a light source powerful enough to be visible for a few weeks from the star closest to the Sun, you would need to harness several thousand times the energy consumed by humanity in a year. Which we can agree is out of reach and doesn't make any sense. A first solution to counter this ability of space to disperse our signals could lie in the use of intense laser pulses, which would concentrate and channel the emitted light rays into very narrow beams in order to minimize the loss of signal in space as much as possible. The problem is that even so, the amount of energy needed to make such a beam detectable is absolutely enormous. It is estimated that it would take the equivalent of the energy produced by a nuclear power plant to generate a laser beam that remains detectable without having advanced technology up to several dozen light years from here. Beyond that, the gradual dispersion of the beam and its loss of intensity make it unrecognizable. Because in the interstellar medium, the faint presence of molecular gas and dust slightly disrupts the propagation of light and the nature of its waves. And after years of enduring these small disturbances over great distances, they end up having immense consequences, to the point of distorting or even completely erasing the original content of the messages sent. In addition, on top of these obstacles, building lasers that are both powerful and precise represents a colossal technological challenge and would cost a fortune. So how can we make sure that the message we're trying to share, whether it's instructions for mastering one of the worst inventions ever created by a species in the universe, namely the alarm clock, or a question about the meaning of life, reaches its destination without being erased? Well, luckily for us, when you want to send a message at the speed of light, you're not limited to just the part that we can see. You actually have plenty of options, because you have the entire electromagnetic spectrum at your disposal, ranging from very low-frequency radio waves to high-energy gamma rays. And since each part of this spectrum has unique properties that affect how these waves travel, we can look for the optimal channel to make ourselves heard by extraterrestrials. Among all the types of light that exist in the universe, the waves located at the lower end of the electromagnetic spectrum, which are grouped together under the term radio waves, have the huge advantage of being able to travel through the interstellar medium without being significantly degraded by the presence of clouds of gas and dust, while requiring relatively little energy to produce. To send coded greetings toward the cosmos without them being erased before they arrive, it seems perfect on paper. Except that even in the realm of radio waves, the signals sent still need to be powerful enough not to be completely drowned out by the ambient background noise of space. Because the interstellar medium, the space between the stars, is continuously bathed in a flow of electromagnetic radiation invisible to the naked eye, emitted by solar flares, by exotic natural objects such as pulsars or quasars, or simply coming from the cosmic background radiation. This tired light that reaches us from the beginning of time and was emitted when the universe changed from opaque to transparent. In fact, anybody with a temperature above absolute zero continuously emits small amounts of radiation, to the point that it is estimated that out of 100 light particles traveling through space, only 4 of these photons were emitted by stars. And all of these emissions make up a kind of background noise that must be overcome in order not to go undetected. To give you an idea of how the background noise of space can cause signals to fade, consider that the radio waves emitted by the most powerful FM broadcast antennas on Earth must be indistinguishable from the cosmic background noise at a distance of just a few light years, even for radio telescopes as sensitive as the most advanced ones we have. Now, since the intensity of the signal quickly fades as it travels across the vast expanses of space, decreasing with the distance covered, don't expect to be able to flood the entire cosmos with your greetings, even using economical radio waves. Because this loss of intensity with distance has very significant consequences. It means that after a few hundred light years, even the most powerful signals we have sent so far become difficult to detect. To get a sense of this staggering dilution, consider that to send a radio message powerful enough to be detected with technology similar to ours, at a distance of 100 light years from here and in all directions, you would need 7,000 times more energy than the total provided by all the power plants on the European continent, as well as an absolutely gigantic network of radio telescopes to broadcast the signals. That's especially why the signals we send are almost always focused on a specific point in the sky. Which brings us to another difficulty. Sending a message, no matter its content, also requires knowing how to aim well to maximize the chances that it will be received. Because the stars are not stationary relative to each other. They move through the cosmos. And to stay on target, you need to be able to reach moving targets located tens, hundreds, or even thousands of light years away from here. All while firing from a planet, itself in orbit, around a moving star. In fact, it's partly to avoid getting too caught up in the details that one of the most iconic attempts to communicate with extraterrestrials, the so-called Arecibo message, was sent toward the Hercules Globular Cluster, a distant region of the sky where nearly 100,000 stars are concentrated within a region about 150 light-years across. And it's amusing to think that this message, sent in 1974 using an antenna 305 meters in diameter, and which remains to this day the most powerful one ever sent into space. Concentrating the equivalent of the broadcasts of several thousand conventional radio stations into a single narrow beam, it will probably arrive at its destination as a weakened and almost dead signal. If the Arecibo message is sure to arrive in tatters, it's because it wasn't repeated and contains no redundancy to protect it from the erasing effects of space, which over such vast distances will inevitably wipe out parts of it. Intended for a massive cluster of stars located at the dizzying distance of 25,000 light-years from here, the journey is partly erased and destroyed by noise. Yet, it only takes a few bits of information, a few pixels of content, for the entire final image to be stripped of its meaning. Finally, there's one aspect I've kept silent about until now, the precise choice of the radio frequency used for transmission. Because when you look more closely, the range of radio waves is absolutely gigantic. So the question is whether, among all these possibilities, there is a frequency that stands out from the others, one on which it seems more logical to listen and transmit. Which radio frequencies are extraterrestrials most likely listening to? The question may seem absurd to you. Yet, most researchers agree on this point. Extraterrestrials are most likely listening to waterhole radio. I'm the one who named it that. It's not an official name at all. Waterhole radio is the frequency band between 1 and 3 gigahertz, and among the vast range of the electromagnetic spectrum, it is the region unanimously considered to be a potential meeting point. Because on one hand, the clouds of gas and dust in the interstellar medium are generally transparent to these wavelengths, and above all, that's where you find the famous waterhole. It includes the spectral signatures of the elements that make up water, including hydrogen, the most abundant and simplest atomic element in the universe. The underlying idea behind this choice of frequency for transmission is that it could very well be universally considered as a meeting point by other advanced extraterrestrial civilizations who, like us, are trying to broadcast or listen. In total, since we have been able to send messages toward the cosmos, only 12 radio transmissions powerful enough to reach their target have been sent, in the hope that one day it will be picked up and deciphered by another intelligence. If you want to dive into the content of these messages, there's actually an episode dedicated to them right there. And out of these 12 transmissions, most were sent a bit blindly towards star systems about which we know almost nothing. Sometimes we aren't sure if planets exist there. It's like trying to send a letter to the other side of the world without knowing if the address exists or if anyone lives there. If that's the case, they can only reply if they are listening when the message arrives. That they have the desire to open it, to read it, to try to understand its meaning. And all this, decades after the message was sent, without being sure that its content hasn't been partially erased during the journey. In this sense, the magnitude of the challenges to overcome to ensure that our messages survive in the cosmos could help explain why the search for extraterrestrial intelligence is, for now, limited to a deafening radio silence. Maybe they do exist, but our messages are not strong enough to reach them. Or maybe they've picked some up but mistake them for noise or find them baffling. Maybe. In any case, I really like the idea that if one of our messages ever received a reply, we would have to deal with the immense time lag imposed by the staggering distances that separate us from other stars in order to start a conversation. A conversation that would be almost surreal in its slowness, since the time lag between sending questions and receiving answers could be measured in decades. That would give us plenty of time to let our thoughts mature. Thus, any attempt at interstellar communication can only be a long-term project, with discussions that could stretch over centuries and generations. It's Grandpa and Grandma who asked the question, and it's their great-grandchildren who will get the answers. And before I leave you, I'd like to share one last thought with you that I find absolutely mind-blowing. To the question of whether we are the only advanced intelligent life form in the universe, there are only two possible answers. Either we are alone or we are not. And whatever the answer to that question is, the implications are absolutely staggering. If intelligent life exists only on Earth, then we have an enormous responsibility toward it. If it exists elsewhere, then discovering it would be a narcissistic blow that's terribly hard to take. For many of our contemporaries, a god. While we wait to maybe one day receive an answer, our planet is home to 100% of the known forms of life in the universe, since we haven't found any elsewhere yet. Here's a video designed to blow your mind, and it's about the size of the entire universe. And here, a playlist with lots of questions related to extraterrestrials, where you'll find the content of the 12 signals sent toward the stars.